All right, so we are going to continue on with induction. Induction. So really, the emphasis once again is on presenting a lot of examples, but what I want to do first is give a kind of rigid framework which you should use when you're trying to do induction proofs. So remember that an induction proof has two main steps. The first step essentially being the basis step, and then the second step being the inductive step, or how to go from, if you have a statement p to the k, or p of k for all k, well, show that if you have the statement p of k, then that implies the statement p of k plus 1 for all k. So induction is going to give us a process for proving statements p of n which rely on the positive integers, or some subset perhaps of the positive integers. Okay, so a cheat sheet for induction. So when you have an induction problem to solve, the first thing that you should do is express the statement to be proven in terms of these kind of Pn symbols. So express the statement to be proven as P of n for all n greater than or equal to b. So there's going to be some b, which here denotes the base case, the smallest case that you need to consider. And you want to express the thing that you want to prove as, I want to demonstrate that all these pn's are true. Okay, so b, write out basis step. And then you want to show that P of B is true. Usually the basis step is a pretty easy step. It's, you know, in the examples like we were doing last time, it essentially boiled down to showing that 1 is equal to 1 or 2 is equal to 2, right? You have two sides of an equation, and they're in different shapes. One side was a sum, the other side is some closed formula. And you just want to show that if you plug in 1 to both sides, then you get the right thing. 1 or 2, or here, you just need to find the correct base integer b, such that you prove the P of B statement. Okay, the next thing that you want to do is you want to write the induction step and write out pk. So write inductive step. And then write out the statement pk for an arbitrary k. P of k for an arbitrary k greater than or equal to b. So you're just writing out the statement that you'll assume to show that P of k plus 1 is true. Okay, so here the book makes another step, but I want to kind of frame this step as a warning. So this step D, yellow is not very visible. Maybe I'll do it in red. So I would caution you against doing this step literally. So the book then suggests that you write out the statement P of k plus 1. P of k plus 1 statement. So what I want to say here is that it is an important idea to understand which statement you are trying to prove assuming P of K. However, it can be risky to write this down at this stage in the proof because it can very easily lead to circular reasoning, where you inadvertently use the statement that you're trying to prove the statement that you're trying to prove. And that will lead to errors in your proof. So one strategy to do is to write out the statement P of K plus 1 on a piece of scratch paper, kind of write it separately. Try not to actually write it at this stage. You just want to gain some understanding of what statement you want to prove if you assume P of K. Okay, then A, B, C, D, E, prove P of K plus 1 using or assuming PK. So using PK. So if PK plus 1 is true, show that then PK plus 1 is true via the inductive hypothesis. So the inductive hypothesis is the hypothesis that this proposition P of K is true, and then you use that to show P of K plus 1 is true. The book is a little pedantic, but it's not a bad thing in this case. So conclude by saying with this concludes the inductive step. And then finally, G is state the conclusion by induction. P of n for all n greater than or equal to b. And then write your box or QED or whatever. So admittedly, this is a bit rigid. It goes so far as to tell you what to write at different points in the proof. I think that this framework is valuable to adhere to, just because induction is the most involved proof technique that we've learned thus far by a long shot. It involves some very specific ingredients that go into the recipe of a proof by induction, and having a rigid framework that you kind of fall back on can be very valuable. Okay, so what I want to do is I want to, and I don't know if this is legible, this says write out P of K plus 1 statement, but be cautious about that. So what I want to do next is, once again, go through a number of interesting examples and try to adhere to this framework as much as I can. All right. So let's do a first example. Let's prove the following statement. Prove that 3 to the 7th is less than 7 factorial for, prove that 3 to the n is less than n factorial for n greater than 6. Okay? So indeed, our statement that we want to show, so proof by induction, what we wish to show is that this statement right here should be called Pn, right? This statement, 3 to the n is less than n factorial. I get a sequence of those statements for every integer, positive integer. And moreover, I know that I only want to verify these statements or prove these statements are true when n is greater than 6. So my B, my base case here, looks to be n is equal to 7. Usually we've been doing the base case is equal to 1, but you know, there are plenty of problems that require different base cases. So we show that Pn, which is equals 3n is less than n factorial, holds for all n greater than 6. So the B is equal to 7. B is our base case. Okay, that's our first step. We express our statement to be proven as P of n for all n greater than or equal to B. We write out the basis step. So basis step the first thing that we need to check is that this statement, P of n, is actually true for the base case, namely 7. So the base step is verify that 3 to the 7th is indeed less than 7 factorial. But this is true. I calculated this on a computer. Is true since 3 to the 7th is 2,187, and 7 factorial is 5,040. Remember, the factorial means take the integer and then multiply by all the integers that are less than it. So 7 times 6 times 5 times 4 times 3 times 2 times 1. Positive integers less than it. Okay, so the base step is proven, that is P of 7 is true since 2,187 is indeed less than 5,040. Okay, so now I want to write out the inductive step. So I'm going to assume that P of k is true for some arbitrary k greater than or equal to 7. So in particular, what I'm going to have is that for this particular arbitrary k, 3 to the k is indeed less than k factorial. So assume this. We want to show that if we assume this, then P of k plus 1 is true. Now, I don't want to, maybe I'll write out here in the scratch work. Is this visible? This is scratch work. The thing that I want to show, relying on this, is that P of k plus 1 holds, which is 3 to the k plus 1 is less than k plus 1 factorial. Okay, so what I do is I start off with one chunk of this statement. This is a relationship between 3 to the k plus 1 and k plus 1 factorial. So now I examine 3 to the k plus 1. This is one piece of the p to the k plus 1 statement. Well, the first thing that I can do is I want to write this in some form such that I can use the inductive hypothesis. So the inductive hypothesis is that 3 to the k is less than k factorial. So I want some 3 to the k to be appearing here. So this is just equal to 3 times 3 to the k by arithmetic. And this, by the inductive hypothesis, I hope that's legible. By the inductive hypothesis, 3 times 3 to the k is less than 3 times k factorial. Here's where we're using this step. Okay? And now I claim, moreover, 3 times k factorial is less than k plus 1 times k factorial. Why? Because k is greater than or equal to 7, right? If k is greater than or equal to 7, then k plus 1 is greater than or equal to 8, and 3 times a number is going to be less, 3 times a positive number is going to be less than 8 times a positive number. And this can be 8 or larger. So 3 times k factorial is less than k plus 1 times k factorial. But then we've assembled our whole statement. Thus, 3 to the k plus 1 is less than k plus 1 factorial. This is precisely, this is the statement p of k plus 1. So what am I supposed to say explicitly? So this concludes the inductive step. So what we have shown is if we use the inductive hypothesis, 3 to the k is less than k factorial, then that implies that 3 to the k plus 1 is less than k plus 1 factorial. This concludes the inductive step. And then, after we have finished both the basis step and the inductive step, that is sufficient for a proof by induction. So by induction, um, 3 to the n is less than n factorial for all n greater than 6. So that completes this inductive proof. Okay, great. So that's another example. And what I'm going to do next is furnish you with even more examples. The next one is an example which comes from calculus, which is an exciting thing to come back to. I'm going to try to keep this list of steps up above, so hopefully they're visible and you can check that I'm more or less following them and that I should be following them better. Okay, let's do another example. So the next example is going to be harmonic numbers. So as a reminder from something that you saw in Calculus 2, let's let the jth harmonic number, h sub j, be equal to 1 plus 1/2 plus 1/3 plus 1/4 plus all the way up to 1 over j. So the harmonic numbers are just, you take the first j integers and you take their inverses and you add them all up. Okay? So what we want to show, that h sub 2 to the n is greater than or equal to 1 plus n over 2. So I'm showing that these harmonic numbers are bigger than something. Okay, so essentially this is the statement that we want to show. So the important thing to remember when we're starting these problems is we want to find the correct base case. So maybe we should play around with the first couple numbers here. We should find out which numbers make sense. So I claim that actually here we should take as a base case 0. So 0 should be our base case. And that's because if I plug in n is equal to 0, then I'm just getting h of 1. So p of 0, the statement p of 0 is h sub 2 to the 0 is greater than or equal to 1 plus 0 over 2. And indeed, this is correct because h2 to the 0 is the same as h of 1, which is just 1. This is the statement that 1 is greater than or equal to 1. And indeed, this is true. Okay, so this maybe is a little scratch work if I want to do things formally. So proof by induction. We wish to show that h2 to the n is greater than or equal to 1 plus n over 2 for all n greater than 0, or greater than or equal to 0. And we start off by our base case. Base case, or basis step, I suppose. Basis step or base case. And that's exactly the work that we did here. P of 0 is true because h sub 2 to the 0 is equal to h of 1 is equal to 1 is indeed greater than or equal to 1 plus 0 over 2. So the base case is true. So the next thing that we want to do is we want to perform the inductive step. So inductive step. So let k be an arbitrary integer. K greater than or equal to 0. The statement P of k is the proposition P of k is h2 to the k is greater than or equal to 1 plus k over 2. Now, I want to use this to prove the statement h sub 2 to the k plus 1. Right? That's the next integer up after k is k plus 1. Okay, so what I'm going to do is I'm going to write out one side of the p k plus 1 statement. So writing out one piece of the p k plus 1 statement is h sub 2 to the k plus 1. Well, let me write out what this is just so I can kind of see what's going on. This is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus all the way out to 1 over 2 to the k plus 1 over 2 to the k plus 1. Notice that I'm adding not in the exponent, but just downstairs. Plus 1 over 2 to the k plus 2, and so on and so forth, until I get to 1 over 2 to the k plus 1, where now the k plus 1 is in the exponent. Okay? So I've just written out what h sub 2 to the k plus 1 is. And once again, you're probably getting a hang of this game now. I write out one piece of the proposition p of k plus 1, and then I try to find some pertinent information from the statement p of k hiding in there. So essentially what I'm looking at here is that this chunk from 1, the sum from 1 all the way over to 1 over 2 to the k, this is exactly equal to h2k. Okay? And the other statement that I want to notice is I want to count how many terms are in here. And the answer is there are 2 to the k terms left over. So essentially, you can see this by saying if I start by adding up 1, then I add up 2, then I add up 3, then I add up 4, et cetera, et cetera, et cetera. How many integers do I have to add up before I get 2 to the k plus 1? Well, 2 to the k plus 1 should be equal to 2 to the k plus 2 to the k, right? 2 to the k plus 2 to the k is equal to, I'm going to factor out a 2 to the k times 2, which is equal to 2 to the k plus 1. So I'm just saying how many terms are in here? And the answer is there are 2 to the k terms. I'm just holding on to that information. It's not necessarily obvious. This is something that requires mathematical thought, right? This is the step in the proof which demands that you do some genuine mathematics. Okay, but anyway, in any case, I have written out what h 2 to the k plus 1 looks like. And now I have no more room. So let me just take a step here and say, let me pause. Okay, so now I suppose what I'm going to do is I'm going to reuse this board. Where's my chalk? Okay. So what I've gotten so far is I'm working on the inductive step of this problem, and I know that h sub 2 to the k plus 1 is equal to 1 plus 1/2 plus 1/3 plus all the way up to 1 over 2 to the k plus a bunch of other stuff all the way up to 1 over 2 to the k plus 1. This stuff right here is equal to h to the 2k. So what I'm going to do is I'm going to use the inductive hypothesis. So by the inductive hypothesis, this whole sum, is going to be greater than or equal to, the inductive hypothesis said this whole sum is greater than or equal to 1 plus k over 2, this thing. So this whole thing is greater than or equal to 1 plus k over 2. And then here I've got a plus 1 over 2 to the k plus 1 plus 1 over 2 to the k plus 2 all the way up to 1 over 2 to the, in the exponent, 2 to the k plus 1, right? This is by the inductive hypothesis. I'm replacing h sub 2 to the k with a 1 plus, I'm saying this thing is less or greater than or equal to 1 plus k over 2. The next thing that I'm going to do is I'm trying to prove a bound, right? I'm trying to show that this whole statement is greater than or equal to 1 over k plus 1 plus k plus 1 over 2. So since I'm just working with these greater than or equal to's, what I can do is I can replace all of these terms in here. So for instance, 1 over 2 to the k plus 1, this is some number that is bigger than 1 over 2 to the k plus 1, right? 2 to the k plus 1 is a bigger number than 2 to the k plus 1. And so when I invert, when I take a bigger number in the denominator than a small number in the denominator, this number is bigger. So since I already know that my h to the 2k plus 1 is bigger than this number, if I replace this number by a smaller number, I'll still have that h to the 2k plus 1 is bigger than that smaller number. So I'm going to replace, oh no, I'm going to replace all of these numbers individually by smaller numbers, and the relationship will still be preserved. So this whole thing is also greater than or equal to 1 plus k over 2 plus, I'm going to replace 1 over 2 to the k plus 1 with this thing. 1 over 2 to the k plus 1 plus 1 over 2 to the k plus 1 plus all the way over to 1 over 2 to the k plus 1. Right? I've taken some number, h to the 2k plus 1 is bigger than this number, and this number is bigger than this number. So h to the 2k plus 1 is certainly greater than or equal to this number. And now comes the point where I remember how many of these terms there were. There are 2 to the k of these terms. So this whole expression is equal to 1 plus k over 2 plus 2 to the k times 1 over 2 to the k plus 1. I've got 2 to the k copies of 1 over 2 to the k plus 1. And this is equal to 1 plus k over 2 plus 2 to the k over 2 to the k plus 1. If I cancel out the 2 to the k's, I'll be left with 1 over 2. And this is equal to 1 plus k plus 1 over 2. So here it was kind of a long process to go from an expression involving h to the 2k plus 1. We had to say that it's greater than this thing using the inductive hypothesis. Then we had to say that this thing is bigger than this thing. I replaced it by something that is more manageable mathematically. And finally, I get the right-hand side of the statement, p to the k plus 1. So thus, h sub 2 to the k plus 1 is greater than or equal to 1 plus k plus 1 over 2. This is the statement p of k plus 1. Thus, we have finished the inductive step. We have shown that if we assume p of k, we must have the statement p of k plus 1. This concludes the inductive step. Thus, so by induction, h sub 2 to the n is greater than or equal to 1 plus n over 2 for all n greater than or equal to 0. All right, so we have finished the induction proof. And moreover, we've proven an important fact in calculus, namely that the harmonic series diverges. So the harmonic series is what you get when you try to take this sum towards infinity. So you try to make sense of the sum 1 plus 1/2 plus 1/3 plus 1/4, where there's no upper bound to the integers in the denominator. And a very important question is, does this series converge or diverge? And how you examine that in calculus is you look at the partial sums. These h sub 2k plus 1s are precisely the partial sums where the last term has denominator 2 to the k plus 1. And what we've shown is that the h to the 2k plus 1s will eventually be greater than any integer you pick. And this is equivalent to saying that this series diverges. So that's a nice thing to kind of remember from calculus. How much time do I have left? I have about a minute left, and so I can't do my last example, which is a very nice one. Maybe I'll do that at the beginning of the next lecture. I am not sure if this is too many examples or not, but in any case, thanks for watching.